Hi everyone, welcome back to Turning Turing. Today we'll explore a special sorting algorithm called counting sort. It is different from all the comparison based sorting algorithms we've discussed till now, like quick sort, merge sort, insertion, bubble, selection sort. In this video, we'll break down the concept of counting sort, dry run an example, analyze its efficiency, and we'll also go over the implementation for counting sort. The implementation is fairly simple given you understand the concept. So let's dive in. Now, counting sort is a non comparison based sorting algorithm. Instead of comparing elements, it uses a count array to store the frequency of each element. So, what are the steps of this algorithm? The first step is that we find the range of the input data. The next step is we create a frequency count array. So what does this mean? We've already found the range of our input data. Let's say our input data is from x to y. So now we define an array where each index represents an element from x to y. So index 0 will represent element x. Index 1 will represent element x1, x plus 1 till the last index n, which will represent element y. Now we'll store the frequency of each element in this count array. So store the frequency count. So let's say if the element x occurs 2 times in our input data, we'll store 2 here. X plus 1 occurs 0 times, so we'll store 0 here. X plus 2 occurs once in our input data, so we'll store 1 here. So on. Let's say that y occurs 5 times, so we'll store 5 here. So in this array, we would have stored the frequency of all the elements existing in the input array. Now you might be able to see how we are going to use this count array. Obviously, we are going to use this count array to place the elements in a sorted order in our output array. Now we have all the elements that exist in our input array, and we also have their frequency or the count of the number of times they occur in our input array. So now what we do is we prepare our output array starting from x. Based on the frequency, we start putting elements in the output array. So the last step is use the count array to put elements in output in a sorted manner. So let's try to dry run it using an example. So let's say our example is 4, 2, 2, 8, 3, 3, 1. So we can see our range is from 1 to 8. So we define an array representing the elements 1 to 8. So we take an array of size 8. So we have 0 index, 1 index, 2, 3, 4, 5, 6, 7. Yeah. So this is an array of size 8 and it is representing all the elements between 1 to 8. So 0th index represents 1, 1 represents 2, second index represents 3, 4, 5, 6, 7, 8. So we have created an array representing our entire range. Now we start storing the frequency of each element. So element 1 occurs once, so the frequency will be 1. Element 2 occurs twice, so here we'll store 2. Element 3 occurs twice again, so we'll store 2 here. Then element 4 occurs once. 5, 6 and 7 does not occur in the input array, so we'll store 0 as their count. And 8 occurs once, so we'll store 1 here. So we've created the count array. Now there are two ways in which you can use this count array to prepare the output array. One is the standard algorithm way and the other one is the more intuitive way. So let's first discuss how the standard algorithm works. I don't know why they have made it that way. It's unnecessarily complicating things. I don't see any added benefit there, not in terms of space or time optimization or anything. And it makes the algorithm a bit harder to understand maybe. So I don't know, but that is the standard algorithm, so I'll discuss it. So what is the next step in the standard algorithm is we convert this into a cumulative count array. So now we have the counts, we convert it into cumulative count. So 1 will stay 1, 2 will become 1 plus 2, this will become 3. Now next index will be 2 plus 3, which will become 5. Next index is 1 plus 5. Next index is 1 plus 5, so it will become 6. Then 6 plus 0, 6. 6 plus 0, 6. 6 plus 0, 6. And then 1 plus 6 will become 7. So we have got a cumulative count array. Now this is basically representing the index till which this element should come. So let me try to explain it in detail. So the number in this array is basically telling the position of 1 in the output array, but this position is not 0 index, this is 1 index. So to make it 0 index, we'll do -1. So what we are trying to say here is that in the output array, 1 should be placed from 0 to 0. Now this is 3. So what we are saying that 2 in the output array should be placed from 1 to 2. 5 similarly should be placed from 3 to 4. 4 should be placed from 5 to 5. 5 should be placed from 6 to 5. So this essentially does not make any sense because we had 0 occurrence of 5. That's why we have this absurd number. Again, what this is representing is that element 6 should be placed from 6 to 5. Again, does not make sense. Element 7, 6 to 5 does not make sense. What this is representing is that element 8 should be replaced from 6 to 6. So these are the indices where these elements should be placed. So this count, this cumulative count is nothing but telling the indices where you have to place the element. Let me show you how it works. So let's create an output array of size similar to the input array. So our output array will be of size 7, 3, 4, 5, 6. So now we start picking each element from the input one by one, and based on the cumulative array, we'll get the correct position or the correct index where this element should be placed, and we'll place it there. So we first pick 4, which is the first element. So now we check the position for 4. So our array represents that 4 should be placed at 6. So this is one index. So converting it to 0 indexed array. So 0 indexed position. So it is essentially saying that 4 should be placed at 5th index. So another thing we do here while placing the elements is that we decrease this number by 1. So this number is basically representing the maximum index where this element can be placed. So now at the maximum index, that was 5 right now, we have already placed 4. So the next occurrence of 4 will be placed at index 4. So we'll reduce this to 5. Now we pick the next element, which is 2. We check that it says 2 should be placed at index 3. So converting it to 0 indexed, 2 should be placed at 2. And reduce this by 1 because we've occupied the maximum index. So next will be placed before it. Again 2 comes. So we've reduced this by 1. It was 2. Now it says that the next 2 should be placed at index 1. Again reduce it by 1. So this will become 1. What it says that if we get another 2, that 2 should be placed at index 0. Now we have 8. 8 says that it should be placed at index 6. So we place 8 here and we reduce this by 1. We pick 3. 3 says that first 3 should be placed at index 4. So we place it here, reduce it by 1. Next 3, it says that next 3 should be placed at index 3. So we place the 3 at index 3 and we reduce this by 1 to 3. And then we pick the next one. 1 says that our first one should be placed at index 0. So we place it here and we reduce this by 1. So you can see how we have used the cumulative count array to get a sorted array. Now this might sound intuitive to some people, but this according to me is very complicated. So according to me, what we could have done is that we could have simply picked this count array, start parsing it from the start, and start placing elements in our output array. So when we start parsing this array, we see that the first element is 1 and there is one occurrence of 1. So in the output array, just place 1. Then move to the next element, which is 2. You see that there are two occurrences of 2. So in the output array, place two twos. Move to 3, two occurrences again. Place 2 3 is again 4, one occurrence, place it. 5 6 7, no occurrence, so skip them. Come to 8, one occurrence of 8, put 8 in the output array. So you would have gotten the sorted array just using the count array without all the complicated logic. And also you're not saving any time complexity there, because here also you would have to parse this array once, and in this particular case also, to find the cumulative array you have to parse this array once. But again, we discuss the other approach because that is the standard algorithm that we have. Now, what is going to be the time complexity and space complexity? So we have a helper count array, and the size of the count array is equal to the range of the elements. So if the range of the elements in the array is k, then our space complexity is big O of k, because we are making a helper count array which is of size k. And the time complexity for our algorithm will be n plus k, where n is the total number of elements in our input array and k is the range. So why is it n plus k? Because we would have to fill this count array. Filling this count array would take n time, because we would be parsing our input array once. We'll be picking each element one by one, and we'll be increasing the frequency in the count array for each of the elements. So parsing the input array will take time n, and then we would be forming our cumulative count array. Forming cumulative count array, we would have to parse the entire count array once. So the time complexity for that is k. And again, in the next step, we pick each input element one by one, and we form the output array. So picking each element one by one would take time complexity n. Checking its position in the count array is a O1 operation, because you directly go on the index and check the number there. So essentially the third step is also big O of n. So the total time complexity is big O of n plus k. For that other approach also, the time complexity is big O of n plus k only. So let's quickly go through the code or the implementation for the counting sort. So I'm just discussing the implementation for the standard algorithm because that is a bit harder to understand. I think the other approach is very logical and simple. So as an exercise, you can implement the other approach on your own. Here I'm discussing the standard approach. So as we discussed, our first step is that we find the range of the elements that are present in the input array. So when we have the range of the elements available to us, we create a count array. So the size of the count array is equal to the range of the elements present, and then we have an output array. Output array has the same size as the input array. So in this particular step, we are increasing the frequency of occurrence of each element. So if element is 1, we'll be adding 1 at 0th index. If the element is 4, we'll be adding 1 at 3rd index. So that's what we are doing here. So basically we are adding 1 for each frequency. In the next step, we are creating a cumulative count array. Now we are going to pick each element from the input array, and based on what the numbers are there in the cumulative count array, we are going to place the elements in the output array. So picking each element from input array one by one, and then we check that what is the number stored for that particular element in the count array, in the cumulative count array. Whatever the number is present in the cumulative count array minus 1, because we want to make it 0 index. So number minus 1 represents the index where this element should be present in the output array. So we find that index where it should be in the output array, and then we place our current element in the output array. And as we said that this represents the maximum index where this element can come. So once we have used that maximum index, we would have to reduce the index by 1. So in the next step, we reduce the index by 1 so that if the next occurrence occurs, we can place it at this index and then again reduce it by 1. By picking each element and placing it in the output array, the final output array will be sorted. And after this step, we'll have that sorted array. Now, pros and cons of this sorting algorithm. It is very fast for small ranges. So for very small ranges, n will be greater than k. and for very small ranges the time complexity will be big O of n. So the maximum or the most optimized time complexity till now we have seen is n log n. So now we have reduced it to big O of n, and it is a non-comparison based sorting algorithm, where again the cons is that it only works for integer values or discrete values. So if you have values something like 1.01 and 1.06, this algorithm wouldn't work for real numbers, and it is inefficient for very large ranges. So let's say that k was very greater than n, so the size of your count array will become very high. So the time complexity n plus k will be very unoptimized due to the large value of k. And that's counting sort, a unique and powerful sorting technique. So if you learned something new, hit the like button and subscribe for more. Have questions or suggestions, drop them in the comment section. I'll see you in the next video. Till then, stay safe and keep learning. Bye bye.